Very good afternoon, students. Very good afternoon to one and all. How are you all? Am I visible and audible? Ashwin, Pratyusha, and Jainvi Rachur students. Can you able to see my screen? Am I audible? Let me know your answer in the chat box or give me a thumbs up if I'm audible to you guys. Yes. Okay, fine. So, let's continue with the solutions lesson today. So, in the last class, we have been discussing about the Raoult's law, right? So, what is Raoult's law? Can you define? Let me recall this with a question. So, can anyone define Raoult's law? Or can anyone give me the formula for Raoult's law? Any one of you? So, just give a try. So, let's recall this. What is Raoult's law? Raoult's law is applicable for liquid system, and the partial pressure or the vapor pressure is directly proportional to the mole fraction of the substances, right? So that is called as Raoult's law. Suppose if I have to write the mathematical equation, so it will be written as Pi, okay, partial pressure or vapor pressure of I component, it will be equal to Pi naught into Xi, okay. So where X is the mole fraction and Pi naught is the vapor pressure of that substance in its pure form. Okay, so this is what we have discussed in the previous class and we have solved some problems also. So today we are going to see about the ideal and non-ideal solutions. Okay, so the liquid solutions which we have been discussing in the previous class, okay, which we have discussed in the previous class, that can be classified on the basis of Raoult's law as two categories. One is ideal solution and the other one is non-ideal solution. Now coming to ideal solutions. So what is the definition? So the solutions which obeys Raoult's law over the entire range of concentration is called as Raoult's law. So all the solution which is going to obey the Raoult's law formula under all concentration, all range of entire range of concentration is called as ideal solutions. Okay. So what is Raoult's law? How to write the Raoult's law? So how to write the total pressure for Raoult's law? So if I'm having a binary system, okay, so I'll be having two components A and B. So PA will be equal to XA into PA naught, right? So PB will be equal to XB into PB naught. So this is in accordance with Raoult's law. Now, if I have to find out the total pressure, what I have to do? I have to write PA plus PB. Okay. So it will be PA plus PB. So substitute PA, PB values here. You will get this equation. Okay. Pi naught, P1 naught into X1 plus P2 naught into X2. So the same formula is applicable for ideal solutions also because those solutions will obey Raoult's law. Got it? So now I am going to, we have two components A and B, or I can take this as 1 and 2. Okay. So mostly A will be the solvent and B will be the solution. Okay. Now coming to A. Okay. So A is a solvent molecule in which AA interaction is present inside the system. And the B is a solute molecule and BB interaction will be present for that system. So now if we combine these two, A plus B, so in A plus B, what we will have? We will have AB interaction. So in which a solute will interact with the solvent molecule to give a solute solvent molecule. And in that AB interaction will be present. So is this clear? So in case of ideal solution, AA interaction is equal to BB interaction. Sorry, both of them are equal to AB interaction. Okay, clear? So there is no change. So all the interaction remains same. Okay. So in that case, for ideal solution, If you go for the change in enthalpy, which is one of the very important thermodynamic variable, change in enthalpy, so that will be equal to 0 because the initial point and the final point are same. The reactants and products are having the same attractive force. So in that case, what will happen? Delta H will be equal to 0 because H1 and H2 will be equal. Okay. So delta H mix is equal to 0. Okay. And delta V volume, change in volume will also be equal to 0 because the interactions are same. Change in volume will also be equal to 0. Now let's see some examples. So examples are very important for ideal solution and non-ideal solution. Okay. So the examples are solutions of N-hexane and N-heptane. So in N-hexane, can anyone give me the formula for hexane? Can anyone give me the formula for hexane? Very good, Ashwin. It is C6H8. Very good. What about heptane? So hexane is C6H8. What about heptane? Hept means 7 carbon. So C7 and how many hydrogen? 16 hydrogen will be there. Okay, C7 and H16. So these two components are forming a solution and it is an example for ideal solution. Now, the next example is benzene and toluene. What is the formula for benzene? Can anyone give me the formula for benzene? Formula for benzene? Find out the formula for benzene and toluene. What is the formula for benzene and toluene? For benzene, it is C6H6. What about for toluene? So a CH3 group attached to CH3 group attached to the phenyl ring is called as toluene. Okay. So there will be 7 carbon and 8 hydrogen. So this is the formula for toluene. Then coming to the third example, it is bromoethane and chloroethane. Bromoethane formula is C2H5Br and chloroethane means it is C2H5Cl. Okay. So such type of hydrocarbons are forming the ideal solution. So examples are very important. You should know the mixture. Hexane and heptane, benzene and toluene, bromoethane and chloroethane. So these are the components A and B of each solution mixture. Okay, now for example, if I take hexane and heptane, so A molecule is hexane. So for between one hexane molecule and another hexane molecule, there will be some attractive force. Okay, so that will be equal to the attractive force between one heptane and another heptane. Okay, and it will be equal to one hexane, C6H8 and C7H. What I'm doing? It is C7H16. C7H16. Okay, C7H16. So here also the attraction is same between hexane and heptane. You can put. Okay, clear? So in all these cases, the attractions are same. Now coming to non-ideal solution. Non-ideal solutions are the solution which does not obey Raoult's law over the entire range of concentration. So they do not obey the Raoult's law. Now this is the formula for Raoult's law and it will not be equal. Total vapor pressure will not be equal to the sum of the values. Okay. And coming to the solvent molecule, so we have A as solvent again. So there is A interaction present in the solvent molecule and also BB interaction present in solute molecule. And if they both combine, they will form AB type of solution, but the attraction will not be equal. Okay. So since the attraction is not equal, the initial value is different from the final value because of the different interaction. So in that case, delta H mixture. Delta H means change in enthalpy of this mixture. Mixture in the sense solution. Okay, so that will be that will not be equal to 0. Change in volume. Okay, delta V mix is not equal to 0. Okay, so here everything is not equal to 0. Now, this ideal solution is getting classified into two. So there are two types of non-ideal solutions we can say. So one is in accordance with positive deviation, the other one is negative deviation. Non-ideal solution showing positive deviation and non-ideal solution showing negative deviation. So in case of positive deviation, so generally the attraction between AABB is not equal to AB. So that is for non-ideal solution generally. Okay. So if AB interaction specifically if it is less, they are not equal. Okay, they are not equal. But if specifically AB interaction is less than AA and BB interaction, then those system will fall under positive deviation type of non-ideal. Okay. And in case of negative deviation, the other way around. AB interaction will be greater than AA and BB. Okay, AB will be greater than AA and BB. Okay. So if AA interaction is more, AA means initial solvent molecule and the solute molecule. If their interaction is more, then the total vapor pressure will be greater. Total vapor pressure will be greater. Then here it will be lesser. So in case of positive deviation, delta H mixture is greater than 0 and here delta H mix is less than 0. And here delta V mix is greater than 0 and here delta V mix is less than 0. Then coming to one more parameter, delta S, which is change in entropy. So here it is greater than 0. In both the cases, change in entropy is greater than 0. So what is meant by change in entropy or what is meant by entropy first of all? Entropy is nothing but randomness. Entropy is nothing but randomness. Okay. So it is nothing but randomness. So randomness or disorderedness we can say. Okay. So if disorderedness increases, entropy also increases. Okay, if randomness increases, entropy also increases. If entropy increases, the change in entropy will also increase. Means delta S will have positive value which is greater than 0. So in both the cases, change in entropy value will be very, very high. So that's why it is greater than 0. Okay. Then one more parameter we have, delta G mix. Delta G means G is the Gibbs free energy. So delta G means change in Gibbs free energy. Okay. So if delta G is less than 0 or if it is negative, okay, if it is negative, then only the reaction will be spontaneous. Okay. So if delta G is negative, then the reaction is spontaneous. If it is equal to 0, then it is in equilibrium. And if it is positive, then the reaction is non-spontaneous. Okay. So all the components which we have seen, so they will undergo the spontaneous reaction means G value should be negative. That is, it should be less than 0. Okay. So positive deviation will also have delta G less than 0. Negative deviation will also have delta G mixture as less than 0. Okay. So these are some of the points. So 6 points we have studied here in this slide about positive deviation and negative deviation. So let's discuss some more points also. So do any of you have any doubt from this slide? From the difference between positive and negative deviation, students? Is everything okay till now? Shall we proceed with the next slide? Ashwin, Jyoti, Lakshmi, Pratyusha. Am I audible? Friends, can you hear my voice? Ashwin, Jyoti, Lakshmi, Pratyusha, can you able to see me? Yes or no? Okay, shall I proceed with the next slide? So do you have any doubts from this? Okay, let's proceed. So coming to the next point under positive deviation, the examples. The examples under positive deviation are the solution of ethanol and acetone. So in ideal solution, we have seen some three pairs, okay, for under examples, and here under non-ideal solution. So we have two different set for positive and for negative. And under positive, the first example is ethanol and acetone. Okay, so the formula for ethanol is C2H5OH, and acetone is CH3 C double bond O CH3. Clear? Then the next pair is carbon disulfide and acetone. Carbon disulfide means CS2 and acetone is same. Okay. And coming to negative deviation, the examples are phenol and aniline. Phenol means it is C6H5OH and aniline is C6H5NH2. So this is one of the pair. The other one is chloroform and acetone. Chloroform means it will be CHCl3 and acetone we all know CH3COCH. So these are the pairs which you have to study, which you have to memorize. Okay. And now I am going to give you one graph for positive deviation and negative deviation. So here is a graph which we have already discussed in the previous class. Okay, in the under vapor pressure we have discussed this. So in x-axis we have vapor pressure and y-axis we have mole fraction. Okay, and at this point we have only component number 2. Only the mole fraction of 2 is there. Mole fraction of 1 is 0. So we do not have the component of 1 at that point. So that line corresponds to only the pure component 2. So it is P2 naught. Then when you come to this point, here we have only the component 1 and component 2 is 0. Okay. So now at this point what I'm having? I'm having the pure component 1 here. Okay. So the green dotted lines represent the ideal solution line. Okay. And above that, we have a red color line, right? So that corresponds to positive deviation, non-ideal solution. Okay. So if the line is above the ideal solution line, if the curve is coming above, so suppose if I take this particular curve, so this is the line, ideal solution line, and this line is coming above this. So if for with respect to each green color dotted lines, if we are getting a curve above that, then those curves denotes the positive deviation curve. Okay. And if I connect P2 naught and P1 naught, so it will give me the total pressure. So this is the graph for positive deviation. Then coming to negative deviation, so we will get a line below that ideal solution line. Okay, same graph is given here, but the red color line is below the green color dotted lines. Okay, green dotted lines denote ideal, red color denotes the non-ideal solution. So if it is below, if the red color line, non-ideal solution line is below the ideal solution line, then it will be the case of negative deviation. Okay, so this point is very important. Okay, so here we have P1 and P2, and this line corresponds to P1, in which it will be equal to P1 naught into X1, and P2 is equal to P2 naught into X2, and P total will be equal to P1 plus P2. Okay, so the same thing here also. Okay, so now I will move on to one question for you. So we have studied the ideal solution and non-ideal solution, and the types of non-ideal solutions we have discussed. All the points which we have discussed under this non-ideal solutions are very, very important. And coming to ideal, the examples are very important. Definition and examples are very important. Okay. So let's go with one question. A non-ideal solution was prepared by mixing 30 ml chloroform and 50 ml acetone. The volume of mixture will be. So I'll give you 1 minute to solve this question. So try fast and give me the answer in the chat box. So tell me which option is correct. Then we will discuss in the class. So just give a try. Give a try to solve this question, all of you. Okay? First of all, tell me the mixture of chloroform and acetone is an example of which solution? Ideal or non-ideal? Chloroform and acetone is an example for non-ideal solution. Okay. So, and specifically, they will come under negative deviation. So, the mixture of chloroform and acetone is an example of negative deviation. Okay. In case of for negative deviation, the volume will be less. The final volume of the mixture will be less than the initial volume. Okay. So, V mix is less than 30 plus 50. So the V1 is nothing but the volume of chloroform. V1 is nothing but this is component number 1 and acetone is component number 2. Okay. So volume of component number 1 is 30 ml and the volume of acetone is 50 ml. So if I add those two, then the value should be greater than the mixture volume. Okay. So it was equal to 50, 30 plus, 30 plus 50 is 80. So the V mix is less than 80. So which is the correct answer? Option B is the correct answer. Correct answer is option B. So is this clear? Shall we move on to the next thing? So is the types and the two types of solutions under this category clear to all of you? Shall we move on to the next concept? Yes or no? Okay. The next topic is azeotropic mixtures. The next topic is azeotropic mixtures. Okay. So what are azeotropes first of all? So the binary mixtures having the same composition in liquid phase and in vapor phase and boils at a constant temperature are called as azeotropes. What are azeotropes? We will have a binary mixture there. Okay. So this is a container in which I have two components. It is a binary mixture and that component mole fraction, two components mole fraction is XA and XB in case of liquid phase and the composition or the mole fraction I can say. So that is denoted as YA and YB for vapor phase. And if it boils at a constant temperature, then it is called as an azeotrope. Okay. So XA. So this part denotes the liquid phase part. Okay. This is for liquid phase. And this is the composition in vapor phase. So this is the composition of A in liquid phase. This is the composition of A in vapor phase. If XA is equal to YA and if XB is equal to YB. Okay. And if the solution boils at a same constant temperature, then it is called as an azeotropic mixture. Okay. So they will have fixed composition and the separation of the components. The A component and B components are present inside the container. No. So the separation of these two components by fractional distillation method is not possible. So what is fractional distillation? Separation of two liquids. Okay, so two liquids will have different boiling point. So according to the difference in their boiling point, one will come out first and then the other one will come. So that kind of separation technique is called as fractional distillation. Okay, and the separation of components by fractional distillation is not possible in case of azeotropic mixture. Got it? And they behave as a pure liquid. It behaves as a pure liquid also. Okay, azeotropic mixture. And under azeotropes also we have different types. We have two types. So what are the points you have to note down here? So the definition is very important. Azeotropic mixture definition is very important. And all the points which I have discussed is important. The very most important is they will have fixed composition and they cannot be separated by a separation technique called fractional distillation. Okay. And now coming to the types of azeotrophs, we do have two types. One is called as minimum boiling azeotrope and the other one is called as maximum boiling azeotrope. The solutions which are coming under positive deviation system, okay, they are called as minimum boiling azeotrope, and the negative deviation solutions are the one which is showing maximum boiling azeotropes. Okay, so examples are 95% ethanol and 5% water in case of minimum boiling. Very important example. Okay, and the boiling point of this system is 351.2 Kelvin. Now coming to negative deviation, it is a mixture of nitric acid and water. Nitric acid is 68% and water is 32%. And the boiling point here is 393.5 Kelvin. Okay, so the composition, components, A component and B component, and the boiling point for both is very important. They will ask you the example and they will ask you the percentage and they will ask you the boiling point. So both are very important. Okay. So with this, the azeotrophs and the types of azeotrophs is also getting over. So today we have discussed, let me summarize what we have discussed now so far. So the vapor pressure of the liquid is the equilibrium pressure of the vapor above its liquid. Okay. So the vapor pressure concept I have discussed with you in the previous class, and this is just the recall of it. And the partial pressure is, vapor pressure is equal to P naught into mole fraction, and that is Raoult's law. Okay. If I have to find out the total vapor pressure of component 1 and 2, then I have to use this relation. Okay. So now coming to today's session, there are two types of solution. One is ideal. Ideal is the one which is obeying the Raoult's law, and the non-ideal is which does not obey the Raoult's law. And again, they are classified into two: positive deviation and negative deviation. Okay. Now we have discussed about azeotrophs. It is a binary mixture. It is also having two types. One is minimum boiling azeotrope and maximum boiling azeotrope. Okay. So these are the topics which we have discussed today. And these are the topics which we have discussed in the previous class. But the liquid solutions are only getting classified into ideal and non-ideal, right? So that's why I have placed this here. Got it? Clear? Do any of you have any doubts from the ideal and non-ideal and azeotropic mixture which we have discussed today? Is everything clear so far? Say yes or no in the chat box or give me a thumbs up so that I can understand. So shall we move on to the questions? Clear. Thank you so much, Ashwin and Pratyusha, for your kind response. Thank you so much. Try to interact and try to answer whenever I ask some question. Okay. So good. So now let's move on to some questions. So you guys are going to give a try for these questions, which are very easy. Okay, they are very easy only. You don't have to struggle here. So the first question is to you on the screen. The mixture which shows positive deviation from Raoult's law is the mixture which shows positive deviation from Raoult's law is. Can anyone give me the answer for this? Benzene toluene, acetone chloroform, chloroethane, bromoethane, ethanol, and acetone. Which is the answer, students? I told you, no? Examples are very, very important here. Which is the correct answer for this question? Have you all taken down the notes when I am discussing the topic? All of you? If you have taken down the notes by this time, you would have given me the answer, no? Nobody is giving me the answer. Very good. Jyoti Lakshmi is saying yes. Okay, benzene and toluene, if you see, they will fall under ideal solution, right? But this positive deviation will come under non-ideal solution. So the correct answer is option D, ethanol and acetone. is an example for the non-ideal solution which is showing positive deviation. Okay. So shall we move on to the next question? Next is, which of the following statements is correct regarding a solution of two components A and B exhibiting positive deviation from ideal behavior? So we have two components A and B, and they exhibit positive deviation from ideal behavior, and which is correct for the solution which is showing positive deviation. So four options are given. Intermolecular attractive forces between A are equal to AB. So this statement will fall under this statement is for ideal. But we are asked to find out for positive deviation means the solution is non-ideal. So for non-ideal, intermolecular attractive forces are between A and B are AA and BB are stronger than those between A and B. So option B is the correct answer. Delta H 0, delta V 0. So all these are for ideal solution. So only option B is the correct answer for non-ideal solution, which is showing positive deviation. Okay, clear? Shall I move with one more question? So the relation, no, I gave you right for ideal AA and BB will be equal to AB. Whereas for the non-ideal, so AA and BB will not be equal to AB. Okay. So now coming to the next question, the mixture that forms maximum boiling azeotrophs. The mixture that forms maximum boiling azeotrophs. So what is the example we have seen under maximum boiling azeotrope now? Only one example we have discussed under each type, right? So under maximum boiling azeotrope, we have water and nitric acid as an example. Water and nitric acid is an example for maximum boiling azeotrope. So what you have to do, go home and study all the examples which is coming under each topic. Clear? So which one is not equal to 0 for an ideal solution? Which one of the following is not equal to 0? So for an ideal solution, delta V mix is equal to 0, delta H mix will also be equal to 0, and delta P also if you take the observed minus Raoult's law value will be taken, but delta X mix is not equal to 0 because change in entropy is always positive because the randomness increases. If the randomness increases, entropy increases. So change in entropy also increases, means it is greater than 0. It is not equal to 0. So delta V mix is not equal to 0 for an ideal solution. Okay, it's a very easy option. A is the correct answer. Option A is the correct answer for this question. Okay, now coming to the next question. PA and PB are the vapor pressure of pure liquid components A and B respectively for an ideal binary solution. If XA represents the mole fraction of component A, what is the total pressure of the solution? So I'll give you 30 seconds to 1 minute to solve this question. So solve this fast and give me the answer in the chat box. Hmm. Hmm. So Ashwin is getting option D. Yes, Ashwin, your answer is correct. So initially, what we have, what is given here, PA and PB are the vapor pressure of pure liquid components, right? So what is the total pressure? So P total is equal to PA into XA plus PB into XB. So we know that XA plus XB is equal to 1. So what is XB from here? It is equal to 1 minus XA. So let me write PA XA here plus PB in place of XB. Substitute 1 minus X. Now multiply PB to both the terms. Will get PA into XA plus PB into 1 minus PB into XA. So we have XA in both these terms. So before that we have PB. Take that out. Okay. So plus take XA from these two terms and the remaining thing will be PA minus PB. Okay, which is nothing but the total pressure of the solution. So where it is given, so I have solved this using capital A and B, and in the answer it is given in terms of small a and b. So option B is the correct. So Ashwin has got the correct answer. Very good. Very good, students. Now coming to the next question. The vapor pressure of two liquids, P and Q, are 8 and 60 torr. Torr is a unit of pressure, okay? So the total vapor pressure of solution obtained by mixing 3 mole of P and 2 mole of Q would be. So what is given in the question? Vapor pressure is given and the number of moles are given. So from this we have to find out the total vapor pressure. So vapor pressure of P is given as 80 torr and the vapor pressure of Q is given as 60 torr. Okay, and the number of moles of A is 3, which is the number of moles of P. Okay, it is actually B. And the number of moles of Q is equal to 2. Now, using these data, we have to find out the total pressure. So, P total is equal to P A into XA plus PB into XB, right? So, component A is P here and component B is Q here. This is component A and this is component B. So what is the vapor pressure of A? It is 80. So mole fraction is nothing but number of moles of that component divided by total number of moles. Divided by total number of moles. Now for NP it is 3 divided by 3 plus 2, 5. Okay. Plus PB is 60 into 2 by 5. Now if I solve this, what I will get? 16 into 3. And here we will get 12. So 16 into 3 is 48. 12 into 2 is 24. So 48 plus 24 is 72 torr. So option A is the correct answer for this question. Okay. Clear for all of you? Any doubt for anyone? Good afternoon, JNV Shimoga students. You have joined late, it seems. What happened? Yes, students, we will move on to the next question, okay? Formation of a solution from two components can be considered as for pure solvent, separated solvent molecule, it is delta H1, and for pure solute, it is delta H2, and for solvent and solute, it is delta H3. Solution so formed will be ideal if for an ideal solution, for an ideal solution, what we have studied, delta H mix is equal to 0 for an ideal solution. Delta H of the mixture will be equal to 0. So if it is equal to 0, then from Hess law, delta H is equal to delta H1 plus delta H2 plus delta H3. Okay. So which is the correct answer? Option B is the correct answer. So delta H of the solution is equal to sum of the enthalpy value. Got it? So moving on to the next question. According to Raoult's law, the relative lowering of air pressure for a solution is equal to. So according to Raoult's law, the vapor pressure is equal to Pi naught into Xa, right? So this is the vapor pressure of the pure component and this is the mole fraction of the solute, right? So Xi, mole fraction of the solute. So the vapor pressure is directly proportional to mole fraction, or we can say it is equal to mole fraction. So option C will be the correct answer. Got it? The relative lowering of vapor pressure for a solution is equal to the mole fraction of the solute. Now coming to one more. An ideal solution is formed when its components. What is the answer for this? For ideal solution, what are the points we have discussed? Delta H mix was 0, delta V mix was 0. So change in volume is also 0, change in enthalpy is also 0 and change in volume is also 0. So coming to option 1, have no volume change, so it is also correct. Have no enthalpy change, that is also correct. So what is the correct answer here? They have both the above characteristics. So option C is the right answer for this. So an ideal solution will follow the first two statements. Clear? Any doubt? Is this okay? So this is the condition which you have to keep in mind for ideal. And for non-ideal, everything will be not equal to 0. So I mean these two will be not equal to 0. Delta S is greater than 0 and delta G will be less than 0. So all these will call for delta G will not equal to 0. Delta H is not equal to 0. Delta V is also not equal to 0. So this is for non-ideal. This is for ideal. Okay. So moving on to one more question for today's session. All form ideal solution except all form ideal solution except. Now you have to give me the formula. So this question is give me the answer. So this question is based on the examples which we have seen under ideal and non-ideal, right? So find out the answer from this by seeing the examples which you have written in your notebook. Just give me the answer here. First we have benzene, C6H6 is benzene. So this is benzene and C6H5CH3. So it is called as toluene. Okay. And C2H6 is ethane. And C2H5I is iodoethane. It is iodoethane. C6H5Cl is chlorobenzene. And C6H5Br is bromobenzene. C6H5I is iodoethane. And C2H5OH is called as ethanol. Now, which will not fall under ideal solution? So, in ideal solution, the attractive forces will be equal. Which will be the correct answer? Any idea? Has anyone got the answer for this? So, the correct answer is option D. So, why option D is the correct answer? We have one of the component here as ethanol. So the formula is CH3CH2OH or C2H5OH. Okay, so here we have a hydrogen bond. Here there is a formation of hydrogen bond between two molecules of ethanol, which is very, very strong. Okay, so one ethanol can form the strong bond with another ethanol. So here if I take this AA interaction is very, very strong compared to BB interaction. Compared to BB interaction. Okay, so in that case, AA will not be equal to BB and both will not be equal to A and B. So AA is different from BB and both will not be equal to AB interaction. So if this is the case, then the solution will fall under non-ideal case, which is an exception for ideal. All form, the first three form ideal solution, but the last one will not form ideal. It will form a non-ideal solution because of the strong hydrogen bond which one ethanol is making with another ethanol molecule. Okay. So is this clear? Any doubt? So with this, I would like to wrap it up the ideal and non-ideal solution part of today's session. So do any of you have any doubts from the topics which we have discussed today? From azeotropic mixtures and from ideal and non-ideal solution? So from tomorrow onwards, try to join on time, okay? And JNV Shimoga students, you have joined very late today. Is there any specific reason? Okay, fine. Now only one more school is joining. I don't know which school it is. Okay, students, then meet you all in the next session. Thank you so much. So in the next session, mostly we will be doing colligative properties. Okay, so we will go with that. So thank you so much for listening to the lecture. Take care. Bye bye. See you in the next class. Yeah, thank you so much, Ashwin.